Welcome back everyone to the 16th lecture of Spatial Statistics and Spatial Econometrics. In this lecture, we will make a formal break from spatial statistics and start to focus on spatial econometrics. Within spatial econometrics, we will begin with what is called as the spatial regression analysis. Spatial regression analysis will provide us an opportunity to conduct multivariate statistical analysis. What does it mean? We will see in a minute, and we will sort of while we sort of kick off this module, we will do a review of the traditional regression analysis for all of you who may not have seen or studied regression analysis earlier. We will go over the basic material, and I will provide you references which you can go back and read if in case you want to learn any of these subtopics in traditional regression analysis in depth. We are not only covering this review of regression analysis which is non-spatial in nature for just sort of doing a recap of it, but also this recap will provide us an opportunity to learn where exactly does spatial regression analysis depart from regression analysis. Just like in case of statistics, we always started with a traditional statistic and then we found points of departure from there, right? So we will look at crucial assumptions of traditional regression analysis. We will study this pathway from correlation or association to causation, and also we will look at the impact of heteroscedastic errors on the least squares estimator. So we will talk about these things. If you have not heard of these terms, there is nothing to worry about, but this is very crucial to also learning where does spatial dependence show up in regression analysis. Then we will move on from this non-spatial regression to a spatial regression, where we will look at the specification of spatial dependence. What are the alternative ways of specifying spatial dependence in regression models? Then we will study the estimation of model parameters in the presence of spatial autocorrelation or spatial dependence. And finally, we will think about causal inference in a spatial regression, right? So we will review these things. Towards the last sub-module within spatial econometrics will be about this idea of spatial lags in order to account for spatial dependence. It is a convenient specification for specifying spatial dependence in regression models, and it allows us very powerful interpretations of how spatial spillovers can impact the processes, the random processes that we see around us in the real world. Okay, within that we will talk about something called a spatial weights matrix. We will look at some of these spatial dependent summary statistics, specifically the Moran's I, the Geary's C, which are based on the definition of this spatial weights matrix. Then we will study regression analysis in presence of spatial lags, and finally we will introduce hypothesis testing. We will ramp you up, and then of course there is a large literature to be explored at your own time. Okay, so let's get started with a review of regression analysis. All right, so when I do that, what I want to do is I want to sort of start with a mathematical formulation of a regression model and also a graphical representation of a regression model. So among the within regression analysis, we have something called as the simple linear regression model. Okay, the simple linear regression model goes as follows. It's y equals beta 0 plus beta 1 xi plus ui, where I grows from 1 to n. So we have a data set of yi's. These yi's could be groundwater levels, something that we have looked at quite extensively throughout this course. But also we could now sort of think of a newer example, let's say the price of homes, right? I mean, when we started this lecture series, we studied or looked at these spatial real estate phenomenon for the National Capital Territory of Delhi. And at the time I had said that we want to be able to explain what goes into this phenomenon as it comes up in space, or as it shows up in space, right? So from that standpoint, going forward in this module, we will take the example of, home prices. So let's say we take an example. Let's specify the example of home prices or house prices. So that means that yi is defined as some price value of a home, ith home in a given communities or in a city or a state or whatever. Okay, and we have n such homes to study, and these homes, as we view them, the prices of these homes, as statisticians and econometricians, we are going to view them as random processes, right? So we are going to say that yi, or let's say we can say pi, is represented by a probability density function f of pi, right? It could be a normal distribution, it could be a, it could be anything. If it's a parametric distribution, you will have a, a parameter, the density parameter, f of theta, right? But the idea is that pi can take multiple values, right? Each home, each ith unit of analysis can take multiple values as far as their price is concerned, and it's going to be drawn from this PDF f of pi, right? So there is some variation in the PIs, and the regression model, what it wants to do, it wants to explain this variation using a variable xi, right? So yi by itself is called as a predicted dependent, or the response, a response variable. We want to explain the variation that is, the PDF, that is the true PDF. We want to explain its properties using a covariate xi, right? Now, when I said covariate, all I meant was xi by itself is called as a independent variable. It's also called as an explanatory variable, right? It's a variable that explains variation in pi or yi, right? It is also called as a predictor variable. It is called as a control, and it's also called as a covariate of yi, right? Okay, all right. So this portion, this particular portion of the regression, that is beta 0 plus beta 1 xi, if you realize is a systemic source of variation in yi, right? It's a systemic source of variation in yi. Why is it called systemic? Because it is a it is a tangible source of variation. So if xi varies a little bit more, pi will vary a little bit more, but I can measure that change, right? I can observe and measure xi. I have data for xi just like I have data for yi, right? So what would be a good example of xi? Xi would be a property of the home. Let's say how spacious it is. We can include an index of this spaciousness of a home or a house by looking at the number of rooms in that house, right? So we can say xi is number of rooms in house I, right? So that means we can say this is Ri, right? So we are writing a model where we are trying to explain variation in pi using a separate variable Ri, right? So there is a systemic portion, systemic component of variation that is going to be the one which is our modeled variation, right? And what remains which we could not explain through xi is called as the model error, which is called as the disturbance or error term. Okay, this is a random source of variation, right? Now, random source of variation is critical to regression analysis, right? Why is that? Well, it's because the way I sort of articulated, we say, okay, as an econometrician, if someone tells me, can you explain the variation in PI in a given community? Why are some homes less price? Why are some homes of high price? And so on and so forth. Why do we see the type of spatial data patterns or simple non-spatial data patterns in terms of why are all homes, in the world not priced equally? Well, it can then be explained by a systemic portion, but as an econometrician, I must view the prices of homes as random variables, right? As random variables. Now, where is this randomness going to arise from in my regression model? It's going to be embedded in this term UI, right? Whatever is xi, that is number of rooms in a home, that variable is non-stochastic or non-random in nature. When I say that a home has 4 rooms or 3 rooms, I don't mean that it's 3 plus minus 2, right? I don't mean it's 4 plus minus 0.2, right? I mean 4 rooms when I say Ri equals 4. So that's a degenerate form of explaining the variation in PI, right? And the source of randomness is this disturbance or the error term which my model could not explain. So, right, we cannot be perfect in explaining every real world phenomenon, right? So, in that spirit, the regression model has 2 components. One is called a systemic portion, which is the modeled portion. The modeled portion has an independent variable and it has what are called as the model parameters, right? In this case, we have the intercept, that is beta 0, and we have the slope, that is beta 1. Why are they called what they called? Let's look at that below. Okay. So now let's conceptualize these data. So we have a data set. Which comprises of columns PI and RI. So I have data, right? So I have prices for, let's say I have I's are the IDs of homes, and I have, let's say, data for 1000 homes, where I have for each home a price level PI and a corresponding, number of rooms or the space over which this is built, let's say indexed by Ri. Okay. Then with these data, I can definitely conceptualize a scatter plot of PI versus Ri. Let's say that scatter plot for these 1000 data points looks like the following. Of course, this is not a perfect plot, but I'm trying to and plot it. Okay. So let's say the number of rooms could be 1, could be 2, could be 3, could be 4, could be 5, could be 6. Let's say maximum there are about 8 room homes, huge homes that we are looking at. Now, what a regression is doing, the systemic portion of the regression is saying that this PI can be explained by a real number line which has an intercept beta 0 and a slope of beta 1, right? This is a regression line, right? But for every given xi, let's say when xi equals 3, if I go and look at the graph, the model will give me beta 0 plus beta 1 times 3 as the systemic component of PI. This is the modeled version, the regression model version of PI. The true PI, however, is not the same. The true PI for this one lies either here or it lied, here. In that case, this distance between the truth and the modeled version is my error representation. Okay. Remember also that here beta 0 and beta 1 are a data driven, understanding of what the intercept and the slope should be. So if I have data driven representations, I use this terminology hat. Okay, if I estimate or predict these parameters, to be predicted or estimated, once I estimate them using the data, the intercept and the slope are called as beta 0 hat and beta 1 hat, because they are no longer the true model. They are no longer the parameters of a true model, but they are the data driven estimates of what beta 0 and beta 1 would be if I were to believe that yi is indeed going to follow the true model that I have specified as an analyst. Okay, so this gives you a gist of what a regression model is. It's at the end of the day, it is a linear regression equation, right? When I say linear, it means linear in parameters, right? If I were to include xi squared here, it will still be a linear regression model because it is linearity between y's and betas, the model parameters and the dependent variable. So the linearity is not between y and x in a linear regression model. Okay, it's very important as a review, from review point of view. Okay, all right. So this gives you a gist of what a regression model is. How does it view the world? What are we trying to really explain here? We're trying to explain variation in prices that we view in real world data sets. The fact that all these prices are different for different homes. They can be, they can be ideally unique for each home. But then what explains this? Well, one thing that could explain is how big is the home that we are trying to price in a market, right? So that's the way to sort of conceptualize it. There is a regression equation. The regression equation has a systemic portion, a non-stochastic portion, and a stochastic or a random portion or a component, right? So ui is random in nature. At every xi, ui can be a different value, right? And the fact that yi was viewed by an econometrician as a random variable is contained in this error term, which is ui. So a part of it is deterministic, fine, but a part of it which remains, which I could not explain with xi, is obviously explained by ui, which is the error term, but the error term is random in nature, right? So that's the basic premise of a regression model. Now, obviously, the linear regression model is a bit restrictive. It only has one regressor. Now, price of home is not only explained by the number of rooms. It is also explained by things like amenities around, right? Number of parks in the community, right? What is the quality of schools, in that community? What is the state of public infrastructure, roads, and crime, control or kind of security, safety, and so on and so forth in that community? What is the access to local, a local market for convenience of residents of that community? There are many factors that drive, how a home is priced eventually in a market, right? Now, a simple linear regression model is one which only has one covariate. In this case, it's xi or ri if yi is pi, right? Now, to be able to relax this restriction, we have what is called as the multiple regression model. Okay. Now, multiple regression model allows me to include more than one covariate. That is, it allows me to include, a general number of many covariates, as many as one analyst thinks, that will explain the, variation in yi. Okay. Again, ui has the same representation, right? So now you have, your systemic component is more complicated. Right? But the error term is still, exactly the same. Although its real world formulation will be different, because now when we included only one xi, let's say x1i, what we did was we put all the other xi's, x2 to xk, into ui. When we included x2 to xk, now ui has whatever is not included from x1i till xki, right? So whatever we exclude from the regression in a simple linear regression, it's all in ui, right? Now obviously, it's a multiple linear regression model because the linearity is between y and all the betas. So now if x2i was, for example, x1i squared and xki was, let's say, x1i to the power k, then you will still have a linear model, right? It doesn't matter how nonlinear is the formulation of x, but what matters is the fact that the model parameters are still linear in y. Okay, so that's a note. All right. The other thing that I want to sort of talk about going forward is that a regression model is links the mean value of yi, that is the dependent variable, with the mean value of xi, that is the covariates. What does that mean? Well, that really just says that, let's say I begin with my simple linear regression model, SLRM. I have yi equals beta 0 plus beta 1 xi plus ui. Now, if I were to take an expectation on this, on both sides of this equation, I'm going to have expectation of yi equals expectation of beta 0 plus beta 1 xi plus ui. Now, the expectation operator is a linear operator, so it will start entering and applying to each term. Here, beta 0 and beta 1 are constants. They do not vary at all. Even across i's, they don't vary. So I have beta 0 plus beta 1 expectation of xi plus expectation of ui. Now, expectation of ui is assumed to be 0 without loss of generality. I will just come to what it means by this assumption of without loss of generality. But the idea is that now what you see here is that the equation, once we assume expectation ui to be 0, this equation is really linking expectation of yi with the expectation of xi, which given the n values is nothing but the sample average of y's and the sample average of x. So what happens is that at the end of the day, a regression model is a model on the mean, right? It is linking the mean value of xi with the mean value of yi. Okay. Now it can happen for, if I go back to my my graph, what's happening is that this regression line is nothing but expectation of pi equals beta 0 plus beta 1. Now these are hats, these are data driven slopes and slope and intercept, right? Beta 1 hat expectation of ri, right? That means that the average of ri, let's say r bar, wherever it touches this line will also refer to the y bar value. And all this is doing is that at every point in xi, I'm actually going and figuring out what is the average y value. Okay, so it's a model on the mean. If I keep xi as variable, then it will be y bar to be figured out at every xi. Otherwise, y bar and x bar will pass through a regression line, right? Now, so this is the representation of a regression. A regression line is a model of the mean values of an estimator. Okay, of the dependent variable and the independent variable. Now, while we explained this, we introduced an assumption right away on which the definition of the regression line is based. The fact that a regression line is a model on the mean depends on expectation ui to be equal to 0, and I have said that we are calling this a without loss of generality assumption. So what is a without loss of generality assumption? In order to move forward, I'm going to start talking about, the crucial assumptions of a linear regression model. Okay, so the first assumption that we are going to talk about is the expectation ui equals 0, which I am calling as a without loss of generality assumption when beta 0 is included in the linear regression model. That is to say that when the intercept is included, then expectation ui equals 0 is a without loss of generality assumption. What does it mean? So let's sort of see what it means. So we have yi equals beta 0 plus beta 1 xi plus ui. Now expectation of yi equals beta 0 plus beta 1 expectation of xi plus expectation of ui. Now say that expectation of ui is equal to a bar. Notice that as long as beta 0 is included, we cannot differentiate between itself and a bar, right? We cannot differentiate between beta 0 and a bar, right? So if we assume a bar equals 0, then any and all of the impact, if this assumption were not true, let's say we assumed a bar equals 0 but it was non-zero, all of that impact will be captured by beta 0, right? If indeed this was a non-negative number, you could simply think of beta 0 as beta 0 plus a, and then you can write expectation of ui equals 0, right? So then any and all of its impact will be captured by beta 0, even if it were, even if a bar were non-zero, a bar was non-zero. Hence, expectation of ui equals 0 is known as a without loss of generality assumption. Okay. Now, we can represent this assumption in vector format. So we can see that now. So A1 in vector form is written as expectation of u equals 0. So u is now a vector which is n by 1 size, because we have ui's going from u1 to un. So this is a column vector, just like an Excel sheet column, going from u1, u2 all the way till un. Similarly, the zeros are also n by 1. Now I can rewrite this as expectation of u1, u2, u3 all the way till un equals 0, 0, 0. Now expectation being a linear operator just enters the vector like if it were a multiple lambda, right? It's just like if it were a constant lambda. It would simply enter, and what will happen, it will apply to each element of this vector. So this means what I'm saying here is expectation of u1, expectation of u2, keep going till expectation of un all of these will be zeros, right? So all I'm saying is that expectation ui equals 0 for all I going from 1 to n. Okay. Now that's it. So this from here to here, what I'm using is that expectation is a linear operator. We've used this property earlier in this course as well, but I hope this will make things very, very clear. So this is a first crucial assumption of a linear regression model. Thankfully, when the intercept is included, this assumption is a without loss of generality assumption. So let's move on to the second and perhaps the most crucial assumption of the regression model, right? I'm going to call it the most crucial assumption, right? And we will see why. We will see why in a minute. I'm going to write down this assumption as expectation ui given xi is 0. What this means is that not only overall the error should, sum to be 0, but for every given xi the errors must sum to 0, right? If I go back to my scatter plot between pi and ri, right? If I go back to my scatter plot, let's say I have again 1000 homes, I have my data, and I'm simply going to now draw a regression line. I know this regression line is on expectation of pi given ri, which is nothing but beta 0 hat, beta 1 hat ri, right? Now, obviously, for every value of ri, the model is suggesting that there is a level of, pi, which this is nothing but expectation of pi given ri, let's say ri equals r tilde. Now this will be r tilde, right? But for every ri, you have to understand that there is a predicted value and there is truth. Now the truth can be different. So for example, the truth is here and the predicted value is given by the green dot. The distance between the two is the error of the model. It's that error model error, right? So every point, every data point and its distance from the regression line actually represents an error. Now this error is sometimes positive, it's sometimes negative. The assumption that expectation ui is 0 is basically saying that when I sum these errors throughout my sample, my scatter plot, they will sum to 0. That's A1, that is assumption 1. Assumption 2 is a bit more restrictive. Assumption 2 is saying that for every value of ri that I can find my data for, we will have expectation ui equals 0. That is to say, there is going to be error where the predicted value is an underestimate of the truth, but there is also an equivalent value of the truth where the predicted value is an overestimate of the truth, in a way that this underestimation, overestimation, they actually cancel each other. Okay, that is what this second assumption is trying to tell you. Now, what does it mean? Well, before I go on to what it means mathematically, let me just say that this is a crucial assumption for causal inference. So the impact, just because I have written yi equals beta 0 plus beta 1 ri plus ui, just because as an analyst I have decided to put pi on the left hand side and ri on the right hand side, doesn't mean that the directional relationship is from ri to pi, right? Equivalently, I could have just flipped the model and put ri on the left hand side and pi on the right hand side. Does that then mean that the price impacts number of rooms? Did the market price come before the number of rooms? Well, no, it didn't, right? Now, how do you decide the directionality? How do you decide the impact that you are seeing is indeed from ri to pi, right? to be able to say that the assumption in front of your screen is needed, right? If expectation ui given ri is not equal to 0, beta 1 is not providing a causal impact of ri on pi. It is merely a correlation or association between pi and ri. Okay, so if I were to just look at a correlation metric and not even specify a regression, I would have been fine, right? The pain that I'm taking to come to the regression analysis or regression modeling is to be able to work with this assumption, which is expectation ui given ri equals 0. Okay, now let's see how this assumption, mobilizes causation. Now, so let's write down our model of interest. Pi equals beta 0 plus beta 1 ri plus ui. Now beta 1 is nothing but del pi by del ri. As an interpretation, beta 1, as an English interpretation, beta 1 provides a measure of increase in pi upon a marginal change. Remember, marginal change means the delta change in ri. Right? That is, ri goes by a unit 1. Well, we are talking about number of rooms, so you can't have half a room or a 1/4 of a room or 1/8 or 3/8 of a room. If you have another room, you have another room, right? Okay. And this relationship will hold at all levels of ri, right? It doesn't differentiate if I'm going from a single bedroom apartment to a double bedroom or a three bedroom or a 4 bedroom or so on and so forth. This specification, pi equals beta 0 plus beta 1 ri, provides me a beta 1 change in pi upon a 1 unit change in ri. Now see that the above interpretation crucially relies on the assumption that expectation ui given ri is equal to 0, right? To be able to see that, let's say you have pi equals beta 0 plus beta 1 ri plus ui, and pi tilde when ri goes from ri to ri plus 1, and I have a new error variable ui tilde, right? Then pi tilde minus pi is attributable. This change is attributable only to ri delta ri equals 1 if ui tilde minus ui is equal to 0. That is to say that the error term, the change in error when we move on from a smaller house to a bigger house, nothing changes in ui, nothing changes in this unobserved, uncaptured error term of the regression model. If indeed, if you had a situation where ui minus u tilde is not equal to 0, then we cannot say that this change, this change in, pi tilde minus pi is not attributable solely to delta ri. Rather, it will be confusing. Where is it coming from? Is it coming from a change in rooms, or is it coming from that unobserved factor sitting in ui? Now the question is, what would be that unobserved factor? Let's continue that in the next part of this lecture. Thank you.